Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 8 on inverse functions. All right, now I'm hoping that you saw our last lesson on one-to-one functions because we're going to be building on that today with inverse functions. So let's jump right into them. All right, invertible functions. All functions convert inputs to outputs. You've heard me say that a million times. Sometimes, though, the action of a function can be reversed to find the input that gives a particular output. These types of functions are known as invertible functions. Now, let's start in exercise 1 and just look at two kind of random functions that have a relationship with one another. Let's check it out. Exercise 1. Consider the two linear functions given by the formulas f of x equals 3x plus 7 over 2 and g of x equals 2x minus 7 over 3. Letter A, simple enough. Evaluate f of 5 and g of 11. All right, well, why don't you go ahead and pause the video now and do these two evaluations, and I would even suggest doing them by hand. Take a moment to do that. All right, well, let's do it. F of 5, simple enough, 3 times 5 plus 7, all divided by 2. That's going to be 15 plus 7, which is 22, divided by 2. And that gives me 11. Let me do g of 11. That's going to be 2 times 11 minus 7 divided by 3. That's going to be 22 minus 7, which is 15 divided by 3, and that's 5. All right, fair enough. So f of 5 is 11 and g of 11 is 5. All right, letter B. Evaluate f of 0 and g of 3.5. All right, a little bit messier because of the g of 3.5, but I think it should still be able to happen. If you need to, use your calculator, but pause the video now and try to evaluate those two. All right, let's do it. F of 0 is 3 times 0 plus 7 divided by 2. That's going to be 7 divided by 2, and that's actually 3.5. All right, and g of 3.5 is 2 times 3.5 minus 7 all over 3. And that's 7 minus 7 all over 3. And that's 0 divided by 3, and that's 0. So f of 0 is 3.5, and g of 3.5 is 0. Also, something seems a little bit odd there. All right, let's do a composition problem in letter C. Evaluate f of g of -1. Now remember, it's been a few lessons since we did composition. This means I want to do g of -1 first, get an answer, take that answer, and then substitute it into f and get a final answer. So pause the video now and do that composition. All right, well, let me first do g of -1. So that's going to be 2 times -1 minus 7 over 3. That's going to be -9 over 3. And that's going to be equal to -3. -3. Boy, it just barely fits. F of -3 is going to be 3 times -3 plus 7, all divided by 2. That's going to be -9 plus 7, which is -2 divided by 2. And that's -1. So f of g of -1 is -1. All right. How about letter D? Evaluate g of f of 3. At least I've given you a little more space here. Why don't you go ahead, pause the video, start by doing f of 3, get an answer, put that answer into g, and see what you have as the final answer. All right, let's do it. So f of 3 is going to be 3 times 3 plus 7, all divided by 2. That's 9 plus 7, which is 16 divided by 2, and that's 8. And then g of 8 is going to be, let me scroll back here, 2 times 8 minus 7 divided by 3. That's going to be 16 minus 7, which is 9, divided by 3, which is 3. So g of f of 3 is 3. So what appears to be true about these two functions? F of 5 is 11, g of 11 is 5. F of 0 is 3.5, g of 3.5 is 0, right? G of negative 1 is negative 3, and f of negative 3 is negative 1. F of 3 is 8, and g of 8 is 3, right? What appears to be true about these two functions? It might be even hard for you to write this down, but pause the video now and see if you can say what's going on here. All right, well, it's pretty simple. When the output of one function is used as the input to the other function, we get back to the original input, right? So when the output of one function is used as the input of the other, we get back to the original input. In other words, it's almost like these functions are undoing what the other function has done. 5 goes into f, what comes out is 11. 11 goes into g, and what comes back out is 5. So it's like a cycle. 5 gets mapped to 11, 11 gets mapped back to 5. 0 gets mapped to 3.5, 3.5 gets mapped back to 0. Negative 1 gets mapped to negative 3, negative 3 gets mapped back to negative 1. It's like whatever f is doing to the input, g undoes it to get back to the original input. So where does this leave us? It leaves us with the idea of inverse functions. The two functions in exercise 1 are examples of inverse functions. Inverse functions reverse the actions of each other, literally switching the roles of input and output. The general idea is shown in the diagram below. Let's kind of like really look at this, right? So forget about like the second function. You know, you got some function f, right? It's got a domain, it's got a range. And let's say f takes the number a or the value a or whatever, and it maps it to the value b. Its inverse then will take b and map it back to a. Literally, inverse functions simply reverse the roles of inputs and outputs. The domain of f becomes the range of g, the range of f becomes the domain of g. And they just undo each other, which is really quite important, right? Because a lot of times, if you've got a function that acts on an input, you might want to be able to undo what that function has done to get back to the original input. Let's take a look at exercise 2. The functions f of x and g of x are inverse functions. A table of values for f of x is shown below. Draw a diagram that justifies why g of 14 must be equal to 7. All right, well, let's do this together, right? G of 14 must be equal to 7. Well, it's this simple. If I've got x equals 7 and I plug it into the function f of x, what comes out is an output of 14. Now if I take 14 and I plug it into g of x, what must come back out is 7, right? So g of 14 must be equal to 7. Now let's take a look at letter b. Use the idea from a to fill in the table for g of x. Well, again, this is really cool. If I think about f of x, negative 3 goes into f, and what comes out is negative 16. That means if negative 16 goes into g, what must come out is negative 3. Same song, second verse. If 0 goes into f of x, what comes out is negative 7, And if negative 7 goes into g of x, what must come out is 0. Now, if you're saying to yourself, well, to fill in this table, all I have to do is take all the x's and the y's and reverse them, you are completely correct, because that is exactly the idea of inverse functions. One function takes these x values and maps it to these y values. The other function then has to take these y values and map them back to these x values. So 5 would go to 4, 14 would go to 7, which we've already talked about, and 20 would get mapped to 9. Switch inputs and outputs. That's it, right? Switch domains and ranges. X's become y's, y's become x's, domains become ranges, ranges becomes domains, etc. Inverse function notation. When a function has an inverse that is also a function, we'll get into that more in the last exercise, we have a special notation that is used to designate the inverse function. And let me bring this just up to the top. Inverse function notation. If the function f of x has an inverse that's also a function, then we call it f with a little negative 1 of x. Although inverse function notation uses a negative 1 in the exponent position, it has nothing to do with exponentiation. All right, so sometimes in math we use particular notation that can be confusing. And I'm sure many of you watching the video are saying it's not sometimes, it's often or always. But regardless of that, this is one that definitely is a bit irritating. If f of x is the original function, then f with a little negative 1 exponent here of x is its inverse. And trust me when I say it has just nothing to do with exponents. It really doesn't. And we could dig deep and talk about inverse and inverse reciprocals and things like that, but let's not go there. Let's just get into this inverse notation. Exercise number 3. The graph of f of x equals 2/3 x minus 2 is shown below, along with a select table of values. Letter A, create a table of values for this function's inverse. All right, awesome. Well, we just saw how that was done in exercise 2. It should be pretty easy if you were paying attention. Why don't you go ahead and take a few seconds to do that? All right, well, to just reiterate, if negative 3 gets mapped to negative 4 using the function, then using its inverse, negative 4 has to get mapped back to negative 3. We just switch. If 0 gets mapped to negative 2, then negative 2 gets mapped to 0. If 3 gets mapped to 0, then 0 has to get mapped to 3 in the inverse, etc., etc. In other words, switch the x and y coordinates. That's it. I mean, you don't get any easier than that. And now, let's use that a bit. Letter B. Evaluate each of the following. F inverse of 0 equals, and F inverse of 4 equals. And this should be a piece of cake. Pause the video now and fill that in. All right. Well, we can just literally read this table. F of 0 equals 3, and F inverse of 0 is equal to 3, and F inverse of 4 is equal to 9. Finally, letter C, graph y equals F inverse of x on the same grid. All right, this is simple enough. What I'd like you to do is I'd like you to take these coordinate pairs, negative 4, 3, negative 2, 0, 0, 3, 2, 6, 4, 9, graph them, connect them with a straight line, and the inverse of a linear function will be another linear function, and see what you have. Pause the video now. All right, here we go. Make sure, all right. So it's easy enough, negative 4, negative 3, negative 2, 0, 0, 3, 2, 6, and 4, 9. All right, I really should have a ruler here, but I'm just gonna draw it like that, and then we're gonna call that F inverse of x. All right, so simple enough, right? We just switch the x and the y coordinates, and we graph. So easy. All right, let's take a look at one last one. Functions with inverse functions. Every function has an inverse relationship. Everyone does. But not all of these inverse relationships are functions themselves. All right, now in the last problem, with that linear function, its inverse was also a function, which is why we could use inverse function notation. We should never use function notation for something that is not a function. Never, ever. Hear that, New York State Ed? We should never, ever, ever use function notation for something that's not a function. Anyway, let's take a look at exercise number 4. You know what I'm talking about, many of those math teachers out there. Exercise number 4. Given the function y equals x squared shown graph, do the following. Letter A. Based on this graph, create a table of values for the inverse relationship to this function. All right? So it's simple enough. Let's do a little table. All right. And again, this is a table for the inverse, so I'm just going to do y and x. Now, how do we do this? Well, it's pretty simple, right? We take this point, which is at -3, 9. Maybe I'll just make this very obvious. -3, 9, and we just switch them. So now it's 9, -3. Right? And we could take then this point right here, right? This point here, which is at -2, 4, and we're going to switch them, and we're going to have 4, -2. All right, and we just want to keep doing that. So what I'd like you to do is take each one of the marked points, simply reverse its x and y coordinates, and write down a table of values. All right, well, let's keep going. We have the point here, which is at -1, 1, which would become 1, -1. The point 0, 0, if I switch, doesn't make any difference. Then I have 1, 1. And when I switch those, it also doesn't make any difference. 2, 4 will become 4, 2. And finally, 3, 9 will become 9, 3. All right, great. And letter B, graph the inverse relationship on the same grid. Awesome. Well, let's do this together, right? We have x equals 9, y equals -3. That's going to be right there. X equals 4, y equals -2. X equals 1, y equals -1. 0, 0, 1, 1. Those are already on our graphs. 4, 2. And 9, 3. So we get this particular graph for the inverse. All right. Now let's take a look at letter C. How can you quickly tell the inverse relationship is not a function? So it's an inverse, but it's not a function. Pause the video now and tell me how you can tell very quickly that this one, the second one, is not a function. Well, it fails the vertical line test, right? Now, you could also even just look at the table itself, right? An input of 9 has outputs of -3 and +3. An input of 4 has outputs of -2 and +2. So, right away we can see repeated input values having different output values. And there we have it nice and in red. Letter D. What is it about the original function that causes its inverse relationship to not be a function? Well, pause the video now and see if you can answer. What was it about this function, as opposed to, let's say, the last example where we were looking at a linear function, that causes its inverse relationship to not be a function? And this is kind of cool. The original function is not 1-to-1. The original function is not, I'll write it out in words, 1-to-1. In other words, only one-to-one functions, have inverses that are also functions. Now, of course, this relies on you knowing what a one-to-one function is, but remember, one-to-one functions are functions that have no repeated outputs. Now, if you think about that, right, if you've got a one-to-one function that has no repeated outputs, when you find its inverse relationship, that will be then a relationship that has no repeated inputs and therefore is a function. But if you have a function that's not one-to-one, one that fails the horizontal line test, that will then result in an inverse relationship that fails the vertical line test and therefore isn't a function. So it's really critical. One-to-one functions are primarily important because they have inverses that are also functions. And that is the case in our previous problem when we had a linear function, which was one-to-one, its inverse was also a function. In this case, when we have a quadratic function that's not one-to-one, its inverse is not a function. All right, let's do a little summary. So today we talked about inverse functions, and they're super duper cool, right? Inverse functions are two functions that sort of undo each other, right? If one of them takes x and maps it to y, the other one will take y and map it back to x. Now, for many problems that have to do with inverse functions, the thing that you need to know primarily is that inverse functions basically just switch the roles of inputs and outputs, right? If you have to graph an inverse relationship, take a table of values for the original function and just simply flip what the x and the y coordinates are, and those become the new xy coordinates of the inverse. If I gave you the domain and the range of a function and I asked you what's the domain and the range of its inverse, you could just cross off the word domain and range and flip-flop them, right? So suddenly this domain became this guy's range, and this one's range became this thing's domain, all right? The final thing that we looked at was the fact that every function has a relationship that is an inverse to it. But only functions that are one-to-one, functions that pass the horizontal line test, will then have inverses that pass the vertical line test and are therefore functions themselves. All right, well, we will see a lot more work with inverse functions as we kind of work our way up and talk about different types of function types. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.